Browsing a movie catalog is a low-friction process. Millions can view listings and showtimes simultaneously without issue. But the moment users attempt to secure a specific seat for a blockbuster opening, they enter a highly contested bottleneck where only one person succeeds. BookMyShow forces two conflicting architectures side by side. The discovery workload serves millions of concurrent reads. If a movie listing is 2 seconds stale, it functions perfectly. But the transaction workload requires strict consistency, guaranteeing a physical seat is never double sold. This creates a volatile engineering environment. Users compete under high temporal pressure for artificially scarce resources, and completing the transaction relies on third-party payment gateways that can take minutes to respond. Achieving national scale requires completely divorcing the read-heavy discovery path from the write-heavy reservation path. Running both workloads through a single database connection pool guarantees catastrophic system failure under load. We protect the primary database from the massive discovery read volume by placing a Redis cache layer in front of Postgres. Normally, this handles the load, but a flash sale exposes a severe vulnerability, the thundering herd. If the event's cache key expires, thousands of concurrent reads encounter a cache miss simultaneously. They bypass the cache and strike the database to rebuild the data. The primary database is instantly overwhelmed by the read surge. Queries slow down, connection pools exhaust, and the entire system cascades into a timeout failure. To defend against this, the system implements cache mutex locking. When a key expires, the application requires a thread to acquire a short-lived lock before querying the database. Only one thread is permitted to fetch the fresh data, while all others are served the slightly stale cached version. But for the highest traffic endpoints, the system eliminates cache misses entirely using the XFetch algorithm. This line graph tracks a cache key's lifespan alongside the XFetch formula. Instead of waiting for expiry, XFetch calculates the probability of triggering an early background refresh, factoring in database compute time and the remaining time to live. By tuning the aggressiveness parameter, the algorithm ensures that the massive volume of incoming reads will mathematically force a background refresh before the cache actually drops to zero. Combining mutex locks and XFetch completely isolates the primary Postgres database from read spikes. The system maintains sub-millisecond response times for millions of browsing users without risking a stampede. The write path operates under an entirely different constraint. The system must enforce a strict invariant. A specific seat can be booked by at most one user for a given show. The naive approach uses pessimistic row locking inside the relational database. A user selects a seat, the database locks the row, and checkout begins. But external payments take minutes. Holding transactions open that long exhausts the connection pool, completely blocking new users from booking. To scale, the system must extract the temporary lock out of the permanent database and manage it entirely in memory. We implement a 3-step state machine for seat inventory: available, held, and booked. The ephemeral held state is managed by a Redis distributed lock. When a user selects a seat, the server issues a single atomic command: set the lock key, a unique session token, NX and PX 600,000. The NX flag dictates that the key is written only if it does not already exist. Because Redis operates on a single-threaded architecture, it naturally serializes requests, granting the hold to the first user and safely rejecting any concurrent attempts. The PX parameter sets a strict time to live, in this case, 10 minutes. If a user abandons their shopping cart or closes the app, the lock naturally evaporates and the seat is returned to the available pool, without requiring a separate cleanup process. Offloading this hold state to an auto-expiring memory store is the only viable way to survive high-latency payment gateways without crashing the data layer. Even with memory locks, micro-failures emerge under intense concurrency. If a user requests multiple adjacent seats, the server must acquire multiple locks. If user A grabs seat 1 and user B grabs seat 2, a circular dependency forms. Both freeze. We prevent this by forcing a numerical sorting of requested seats prior to lock acquisition. User A wins the first lock, user B is cleanly rejected. The second major edge case occurs at the boundary of the attainment window. If a user's checkout process takes slightly longer than the 10-minute Redis TTL, their lock drops. a second user can now hold that same seat. If the first user's payment then clears, the system will execute a double booking. To close this gap, the architecture uses an extension probe pattern backed by a token-validated Lua script. When the client submits payment, the backend intercepts the request and fires the Lua script to Redis. It verifies the user session token still matches the lock. As it does, the script artificially extends the lock's expiration by a safety buffer, all before the external Stripe transaction is allowed to proceed. True scale is achieved by structurally engineering deadlocks and race conditions out of the logic flow entirely, rather than hoping edge cases don't happen. Once the external payment gateway successfully charges the user, the system enters the final phase, persisting the confirmed ticket to the database. Having the webhook receiver write directly to PostgreSQL is dangerous. If the database is undergoing brief maintenance or experiences a network drop, that webhook fails and the user's confirmed ticket is lost. We decouple the payment receipt from the database commit by using a durable event stream backed by Apache Kafka. The webhook receiver drops the success payload into a Kafka topic. A worker thread consumes that message, updates the seat status to sold, and executes an ACID commit in PostgreSQL. Only after database confirmation does the worker acknowledges the Kafka offset. If the database goes offline, the transaction rolls back and the offset is not committed. Kafka's exponential backoff automatically retries the delivery, guaranteeing that no purchase ticket is ever dropped. However, Kafka's at least once delivery guarantee introduces a new risk: processing duplicate messages, which could result in duplicate ticket allocations. The system handles this through strict idempotency. The database schema enforces a unique constraint on the payment ID column. If a duplicate Kafka message is processed, it triggers a unique constraint violation. The worker safely catches the error, discards the duplicate, and commits the offset. Combining durable Kafka queues with strict database idempotency isolates the core booking engine from network volatility and external service outages. With the complex backend logic securely in place, we now have to synchronize this global state across the entire end-user experience. As thousands of users interact with the seating map, the interface must update in real time as temporary holds are acquired and released. To broadcast these updates, the platform relies on server-sent events, or SSE, rather than WebSockets. Real-time seat updates are inherently unidirectional, flowing strictly from the server to the client. SSE is highly optimized for this. It runs over standard HTTP protocols, allowing the system to use a Redis pub-sub fanout architecture to push state changes to thousands of clients without the heavy load balancing overhead of full duplex WebSockets. This creates a fully realized, highly decoupled ticketing topology. The discovery path remains highly available, shielded from read spikes by probabilistic early cache expiration and mutex locks. The transaction path maintains strict consistency, protected by ephemeral, memory-based distributed locks and durable, idempotent event streams. Architecting for extreme scale requires strictly defining state boundaries, managing high-contention locks entirely in memory, and operating under the assumption that every external dependency will eventually fail.